I usually get asked a lot of questions associated with these free body diagrams, and it's all associated with a slight confusion about what we're representing on that free body diagram. Remember, what we're doing is we're cutting and freeing a body from anything that it's connected to. So a complete and total free body diagram has to be such that the body has no connection to anything in the world, right? Anything. So in our system that we were just briefly looking at before was this cabling system that supported this 1,000-pound force that was coming from the self weight of the bank of lights that it was suspending. And we went in and we cut various pieces out, and we did talk briefly about what happens to the main body of the cable, that sort of thing. Well, let's look at that a little bit more closely. All right. So when we start off and we've cut, say, one of these joints, and remember, cables are always pulling away from the free body. So now when I replace the effect of the cable, which we say was only in tension, right? The cable has to be in tension. Then when we remove its effect on the thing that's left over, then we gotta show what it's doing to it. So the joint is pulling on the rope, but the rope is pulling on the joint. Equal and opposite, you can think of. Every action, there's this equal and opposite reaction. Right? And so this would have been TAB. Right? Same kind of thing up here at the other end. The joint, or support in this case, is pulling on the rope, and the rope is pulling on the support, equal and opposite. Now mathematically what has to happen is that these are two vectors, and when we paste this system back together, because those are internal, they need to disappear, and that's another reason why these have to be equal and opposite, equal magnitude, opposite directions. Right? Same kind of thing now here for the new rope, which is AC. It's going to be in tension. So the joint is pulling on it, and it's pulling on the joint down here at B. Same thing up here at C, that the joint is pulling on it, and it is pulling on the joint. And then likewise for the other forces, the vertical one being CD, and that one, horizontal one, being CE. Right? So again, note how if we were to paste this back together into the original system, then it's got to be the case that the system comes back together in a way that represents the original. And that means that in the original we had only one place that there was a force that appeared. Oops, that's not very horizontal. There we go, it's a little better. We've got these supports here, and we have a whole system of internal effects that are created all because we come along and apply this 1,000-pound external load. Right, now note, again, when we put these back together, vectorially they disappear, and that's why they don't show up here. Same thing here, bam, don't see it. Same thing here, bam, don't see it. Same thing here, bam, don't see it. And I didn't draw the rest of it, but that's what would happen here and there as well. The only force that shows up is the applied force that's sitting out here. It's the rest of all the internal effects that are keeping the system in equilibrium. Hence this notion of, in statics, we are interested in how bodies respond to forces. And this 1,000-pound force creates then these other internal effects throughout the system.